Wherever you are right now, whatever time it is, the ground beneath you has a story that stretches back almost beyond imagining. You might be lying in a warm bed, sitting in a quiet room, or settling in somewhere still and dark, and beneath you, under the floor, under the soil, under thousands of feet of rock and sediment, there are layers. Layers of time, layers of life, layers of worlds that rose and fell long before anything human ever drew a breath. Tonight, we're going to travel into those layers together. Not quickly, not with urgency, but slowly, the way deep time deserves to be explored. This is a journey through prehistoric Earth, through the age of dinosaurs, through catastrophe and silence, and through the long, patient recovery that followed. It is a story about life's extraordinary ability to fill the world, to change it, and to endure. The Earth you know, with its familiar shapes and borders, its mountain ranges and ocean basins, is just the latest arrangement of a planet that has been rearranging itself for billions of years. Continents have drifted apart and collided. Oceans have opened and vanished. Climates have swung from lush tropical warmth to planet-wide ice. The world has worn many faces, and each one of them was home to something remarkable. What we'll explore together draws on what science has uncovered, the fossils, the rock records, the chemical signatures locked inside ancient stone. But science is not finished with deep time. There are open questions, competing theories, and mysteries that researchers are still working through. Where the evidence is clear, we'll follow it closely. Where it's uncertain, we'll say so. Because the honest version of this story is, if anything, more interesting than a simple one. Before we begin, there's something I'd love to know. Wherever you are right now, whether it's late at night, early in the morning, or somewhere in the quiet middle of the day, leave a comment and let me know. What time is it for you, and where in the world are you listening from? I always love knowing who's out there in the dark. Now close your eyes if you'd like, and let's go back. A very long way back. We're going to start about 252 million years ago. That number is almost impossible to hold in the mind, so let's set it gently aside and simply begin with what the world looked like then, and what had just happened to it. Something had ended, something enormous and terrible and quiet in the way that only deep time can be quiet. The Permian extinction, the largest mass extinction in the history of life on Earth, had just swept through. Estimates suggest that somewhere around 90 to 96% of all marine species vanished. On land, the losses were staggering too. Forests collapsed, insect populations crashed. The great sprawling ecosystems that had filled the Permian world simply stopped. The cause, or causes, are still debated. Massive volcanic eruptions in what is now Siberia poured carbon and sulfur into the atmosphere for tens of thousands of years. Temperatures climbed, ocean chemistry shifted, acid burned through shallow seas, and the world that had existed before, rich, complex and full, was almost entirely erased. Almost. Not entirely. Because life does not give up. It never has. Even in the aftermath of something that catastrophic, survivors remained. Small things, mostly. Hardy things. Creatures that could endure heat or drought, or the chaos of disrupted food chains. And into that emptied world, those survivors began, slowly and without any sense of direction or ambition, to spread out and diversify. This is the world that inherited the Earth after the Permian, and we call it the Triassic. At this point in time, the continents were not arranged the way you might picture them on a globe. They had not yet separated into the familiar shapes we know. Instead, they were still gathered together into a single enormous landmass, a supercontinent called Pangaea. And Pangaea was vast. It stretched from pole to pole, a single unbroken body of land surrounded by one enormous ocean, Panthalassa. The interior of this supercontinent was remote from the sea, in a way no landscape on Earth is today. Rains that fell on coastlines never reached the interior. Massive deserts baked under relentless sun. Temperature swings between seasons were extreme, hotter in summer, colder in winter, more violent than most modern climates. The soils were young and thin, the ecosystems rebuilding, and yet life moved into every space it could find. The Triassic was a period of experimentation. That's perhaps the most useful way to think about it. The catastrophe of the Permian had cleared out so many ecological roles, so many niches, that evolution had an unusual amount of room to work with. Groups that had been modest or marginal before the extinctions suddenly had opportunities, and the reptiles, a broad and varied group, took remarkable advantage of that opening. Early in the Triassic, the world was dominated not by dinosaurs but by other lineages. There were the therapsids, sometimes called mammal-like reptiles, some of which would eventually give rise to the very first true mammals. There were archosaurs, a group that would prove enormously important, giving rise not only to dinosaurs but also to crocodilians and eventually birds. There were etosaurs, heavily armoured plant eaters that looked something like armadillos crossed with crocodiles. There were Rauisuchians, large predators with upright limbs that hunted across the Pangaean landscape. There were phytosaurs, semi-aquatic ambush hunters that resembled crocodiles in shape, though they were not closely related. And there were the rhynchosaurs, stocky herbivores that may have been among the most common animals on land for a time. The Triassic was crowded, in other words, with possibilities, with creatures testing different body plans, different strategies, different ways of moving through a world still piecing itself back together. The first animals we consider dinosaurs appear somewhere around 230 to 245 million years ago, depending on which fossils are included and how exactly the boundary is drawn. They were not impressive at first glance, not giants, not dominant. Early dinosaurs were relatively small, perhaps a metre or two in length, bipedal in many cases, lightly built, quick on their feet. They emerged quietly in the southern reaches of Pangaea, in regions that correspond today to South America and parts of Africa, moving through a world already full of other animals competing for food and space. So why did they persist? Why did they eventually rise while so many of their competitors did not? This is a question scientists are still working through, and the honest answer is that we don't have a single, clean explanation. Several ideas have been proposed. One is that early dinosaurs may have had a more efficient upright posture, with limbs positioned directly under the body rather than sprawling to the sides, which could have made them more energy-efficient movers over long distances. Another possibility is that some early dinosaurs may have had higher metabolic rates than their competitors, allowing them to remain active in a wider range of conditions. There are also suggestions that early dinosaurs were behaviourally flexible, opportunistic feeders, capable of adjusting as environments changed. What we do know is that the Triassic did not end peacefully. Around 201 million years ago, another major extinction event occurred. Again, massive volcanic activity, this time along what would become the Atlantic Ocean, as Pangaea began its long, slow breakup, poured carbon into the atmosphere. Temperatures shifted, ecosystems were disrupted again. Many of those Triassic competitors, the Rauisuchians, the etosaurs, much of what had filled the world alongside the early dinosaurs disappeared. And this time, when the dust settled and the world began again its slow rebuilding, it was the dinosaurs that remained. Not because they were inevitable, not because the story was written that way, but because they had survived, again, when so much else had not. And in the Jurassic world that followed, in a world where Pangaea was beginning to drift apart, where seas were rising and climates were softening, they would find the space to become something extraordinary. When the Jurassic begins, there is no sudden fanfare. The sun still rises over plains and conifer forests. Rivers still unwind slowly across lowlands. But something subtle has shifted in the balance of life. Many of the great Triassic predators are gone. The armoured herbivores that once trundled over the floodplains are mostly gone too. In their place, a different set of animals starts to spread into the open spaces. The dinosaurs are still not yet the towering stereotypes that might come to mind. Many are small to medium-sized, light on their feet, built more like graceful runners than lumbering tanks. But they are diverse, and within this diversity, three broad branches begin to stand out. One branch is the theropods. These are mostly bipedal, mostly meat-eaters, with long hind legs, grasping hands and jaws lined with sharp, curved teeth. Early Jurassic theropods like Dilophosaurus are not enormous by later standards, perhaps 6 or 7 meters in length, but they are sleek, fast, and alert. Their skulls are lightly built, their tails act as counterbalances, they move with a smooth, economical gait, their feet placed one after the other in a narrow trackway, bodies held horizontally, heads poised forward, always sampling the air. Another branch is the sauropodomorphs, the lineage that will eventually give rise to the classic long-necked giants. In the Triassic, many sauropodomorphs were still partly bipedal and modest in size, but in the Jurassic some of them begin to shift into a new form of existence, Their necks lengthen, their bodies enlarge, limbs become more column-like, supporting greater weight. By the middle Jurassic, true sauropods appear. Animals like Cetiosaurus and later in different regions, the ancestors of Diplodocus and Brachiosaurus. They're not just big, they're experiments in being huge, in turning mass itself into a survival strategy. The third branch is the Ornithischians, the bird-hipped dinosaurs, though they are not birds and will not give rise to them. Their hips are arranged differently from the other dinosaurs, their pelvis oriented in a way that tends to support large guts for processing plants. Early Ornithischians in the Jurassic are not yet armoured juggernauts or horned titans. They are small to medium herbivores, some bipedal, some moving on all fours, nibbling low plants, travelling in groups. Over time, this branch will spin off into armoured stegosaurs, and later ankylosaurs, and much later still, the horned and duck-billed forms of the Cretaceous. But in the Jurassic, they are still quiet, early notes in a longer melody. These three groups share something important. Their limbs are pulled in under their bodies rather than sprawling out to the side. Their spines are balanced over their hips. Their joints are shaped to support long strides. This posture allows them to move efficiently, to walk and run without the sideways sway of earlier reptiles. Trackways preserved in ancient mud show parallel lines of footprints marching steadily forward, as if whole herds moved together across the landscape. Posture alone is not the whole story, though. Inside their bones, inside their growth patterns, other clues suggest why dinosaurs did so well. Many dinosaur bones, when sliced thin and studied under a microscope, show a dense network of blood vessels and growth lines that resemble those of modern birds and mammals more than those of typical reptiles. Some species seem to have grown rapidly when young, reaching near adult size in only a few years. This kind of growth hints at relatively high metabolic rates, at bodies running warm and fast rather than slow and cold. It is possible that many dinosaurs were neither strictly cold-blooded nor exactly like modern birds in their metabolism, but somewhere along a spectrum, active, capable of sustained movement, able to cope with cooler nights and seasonal changes. In a world of shifting climates and spreading forests, that flexibility would have been an advantage. The world itself is also changing in ways that favour movement and expansion. Pangaea is beginning to break apart. Long rift valleys open, some of them filling with water to become new seas. As the supercontinent cracks, coastlines lengthen. Moist air from the oceans can reach farther inland. The brutal extremes of the interior begin to soften in many regions. Monsoon-like patterns develop with regular seasonal rains. Ferns and cycads, conifers and ginkgos spread into new belts of green. These changing environments create corridors rather than barriers. Land bridges still connect what will eventually be separate continents. Dinosaurs can move along broad coastal plains, through forest clearings, over river deltas that stretch for hundreds of kilometres. Fossil evidence suggests that related dinosaur groups appear across what is now Africa, South America, Europe, and Asia, hinting at long-distance dispersal when those lands were still closer together. Theropods range widely as predators and scavengers, following the trails of herds. Some remain small, nimble hunters of insects and small vertebrates. Others grow larger, specializing in bringing down bigger prey. Sauropodomorphs spread into areas with abundant plants, taking advantage of their long necks to browse at multiple heights, from low shrubs to the tops of conifers. Their size may protect them from many predators, not through armor or speed, but through sheer scale. Ornithischians experiment with different feeding strategies, some cropping low vegetation, others perhaps reaching higher or specializing in tougher plants, their jaws and teeth gradually adapting. Growth, movement, and metabolism weave together into a pattern of success. A baby sauropod hatches at a fraction of its adult size, vulnerable but capable of fast growth if food is plentiful. Juvenile theropods may occupy different roles than adults, hunting smaller prey and reducing competition within the species. Herding behaviours, suggested by clustered trackways and bone beds, may offer protection and better chances of finding food. Being social, at least some of the time, can be a powerful strategy in uncertain environments. The Jurassic, then, becomes the stage on which dinosaurs move from being one interesting group among many to becoming the dominant large animals on land. They are not alone, of course. Early mammals scurry in the undergrowth. Pterosaurs ride the air currents. Crocodile relatives lurk in rivers and lakes. But on the open plains, in the forests, across the floodplains and gentle uplands, it is increasingly dinosaurs that set the tone of life. They do not plan this. They do not sense themselves as rulers. They simply live, generation after generation, their bodies tuned to movement, to growth, to the slow drift of continents and climate. Their footprints press into soft mud, their bones settle into riverbeds and floodplains, and as the Jurassic world warms and greens, their story spreads with them, outward, across the cracked body of the still separating Earth. As time moves on, the outlines sharpen. The small and medium forms of the early Jurassic give way, in many places, to something else entirely. On some floodplains and forest edges, there now stand animals so large that the mind pauses for a moment just to take them in. In a broad valley, a herd of sauropods moves slowly through morning haze. Their necks rise like living columns above the trees. Their feet press deep, round impressions into damp soil. They are not alone. Around and between them, smaller ornithischians drift like schools of fish, alert and restless, cropping low ferns and cycads. Farther out on the fringes, a theropod watches, head tilted slightly, reading the movements of the mass before it. This is not a random crowd of creatures. It is an ecosystem, a web of relationships that repeats itself in different forms across Jurassic and Cretaceous landscapes. Predators, herbivores, scavengers, insects, plants, fungi, and the quiet presences of early mammals and crocodilians, all fitting together in patterns that are different from our modern world and yet strangely familiar. In many regions, the dinosaurs form the visible framework. Large herbivores shape the land simply by eating. A herd of long-necked sauropods can strip branches, push down saplings, open clearings in conifer forests. Over time, their feeding might create mosaics of young and old trees, open glades and dense stands, paths worn into the soil by generations of heavy steps. Smaller herbivores take advantage of these changes, slipping into new niches, grazing on fresh shoots where giants have passed. Predators respond in turn. Some theropods may shadow migrating herds, not always attacking, but staying within range in case weakness appears at the edges. A sick juvenile, an animal that stumbles near a muddy bank, a hatchling that strays too far from the group. Others specialize in different prey altogether. Quick, mid-sized hunters that focus on ornithischians, or even smaller forms that stalk lizards, mammals, and insects in the undergrowth. Between full hunting and full scavenging, there is a spectrum. A carcass left by a flood, a victim of old age or disease, becomes a gathering point where large theropods, smaller carnivores, crocodilians, and even insects all take their share. The dinosaurs are only one part of this system. Under their feet, insects thrive. Beetles burrow in leaf litter and dung. Termites nibble on dead wood. Dragonflies skim above ponds and slow rivers. Some insects bore into fallen logs, hastening decay. Others visit primitive flowers late in the dinosaur era, beginning the long story of pollination partnerships. Spiders spin quiet traps between fern fronds. Ant-like insects explore nests, carcasses, and rotting vegetation. Early mammals move through this same world in the margins and shadows. Many are small, perhaps shrew-like or squirrel-sized, feeding on insects, seeds, and small vertebrates. They climb, dig, and hunt in places the dinosaurs rarely notice. Inside rotting logs, in tunnels under roots, in the space between rocks. Some may emerge mostly at night, when temperatures cool and the heavy steppes above grow fewer, turning the darkness into their own field of opportunity. They are not contenders for dominance yet, but they are alert, flexible, and persistent. Along riverbanks and in wetlands, crocodilian relatives lie half-submerged, eyes and nostrils breaking the water's surface. They wait for fish, for amphibians, for unwary dinosaurs that come to drink. Their bodies have changed less over deep time than many others. Patient ambush, a powerful bite, a life entwined with water, these strategies work in almost any era. All of this life is tied closely to plants. In the Jurassic, conifers, ginkgos, cycads, horsetails, and ferns dominate many landscapes, feeding vast populations of herbivores. By the Cretaceous, flowering plants begin to spread, adding new colours, scents, and fruits to the mix. Different dinosaurs likely specialise at different feeding heights and textures. Some nipping soft leaves, others grinding tougher fronds, still others reaching into the canopy. Their teeth, jaws, and even gut contents preserved in rare fossils hint at these diets, though the details remain partly hidden. Within these living systems, there is also a quieter story: how dinosaurs raised the next generation. In several places around the world, scientists have found fossilized nesting grounds. Clusters of eggs, arranged in patterns, sometimes layered in multiple levels of sediment, as if used over and over again. In Mongolia, North America, South America, and elsewhere, these sites suggest that at least some species returned seasonally to familiar nesting areas, much as many modern birds and turtles do. Eggs are fragile, and yet they appear in organized clutches, sometimes in ring-like formations or shallow pits. In a few cases, embryos are preserved curled inside, their bones delicate and incomplete. Nearby, scattered tiny bones and footprints hint at hatchlings moving together. For some species, adults may have guarded nests, shading them with their bodies, or adjusting plant material to regulate temperature. Fossils of certain dinosaurs found in brooding positions over eggs, arms outstretched, suggest a level of parental care that feels strikingly bird-like. Beyond the nest, behavior becomes harder to see, but there are clues. Trackways showing dozens of similarly sized juveniles walking together hint at groups of youngsters travelling as a cohort, perhaps with adults nearby. Bone beds where many individuals of the same species died together may reflect herd behavior, though floods, droughts, and other disasters can also gather animals in death. Scientists work carefully with these traces, proposing migration or social structures, while knowing that not every cluster of bones records a family group or a seasonal journey. Hunting strategies live in this grey zone of inference as well. The limbs and teeth of large theropods suggest they could deliver powerful bites and cover ground efficiently. Some species have forward-facing eyes that might have given them better depth perception. Their tails, muscles, and joints point to bursts of speed, but perhaps not marathon chases. Whether they hunted in coordinated groups or mostly alone is still debated. A few mass death sites containing multiple large predators have been interpreted as evidence of pack-like behavior, but other explanations, drought, trapped animals at a waterhole, are also possible. For now, it is safest to imagine a range of strategies, from solitary ambush to opportunistic crowding around shared food sources. Defences evolved in response. Many dinosaurs seem to have relied on size and vigilance. A herd of sauropods, with adults towering over their young, would have been a daunting target. Smaller herbivores adapted in different ways. Some ornithischians developed armor plates, spikes, or tail clubs in later periods, turning their bodies into living fortresses. Others remained lightly built, favouring speed and awareness. Horns and frills in later ceratopsians might have played roles in display as well as protection, signalling strength to rivals and predators alike. Yet even here, certainty is limited. What looks like a weapon may also be a billboard for mating displays or social communication. Over all these interactions, the environment itself sets the rhythm. Seasons come and go. Monsoon rains swell rivers, flooding lowlands and depositing fresh layers of sediment. In dry times, water shrinks into deeper channels and isolated pools, forcing animals to travel farther and gather more densely at remaining sources. Drought can weaken vegetation, thin herds, and open windows of advantage for scavengers and predators. Then, when rains return, plants surge back, and with them, the possibility of growth and recovery. Fires ignite in dry seasons, perhaps from lightning strikes, racing through forests and grass-like plant communities. For animals that can move quickly, fire is something to flee from in the moment and return to afterward. Burned landscapes may sprout tender new shoots rich in nutrients. Some plants are likely adapted to this cycle, their seeds waiting in soil or cones, ready to take advantage of the opened canopy and fresh light. Insects swarm into charred wood. Scavengers search for those that did not escape. Life reassembles itself in slightly new patterns. Weather shifts from day to day as well. Storms roll in from warm seas, bringing heavy rain and wind. Temperatures drop at night, especially inland or at higher latitudes. Larger, more active animals may cope better with these fluctuations, their bodies generating and retaining heat. Smaller creatures use burrows, nests, and tight spaces to buffer themselves against cold and dryness. Snow may fall in some high-latitude regions, even in the age of dinosaurs, adding another layer of seasonal challenge for those that live there. Through it all, there is no single typical dinosaur day. Life in a coastal floodplain, in a dry interior basin, on a forested island, or in a high-latitude woodland would each feel different. Yet the same themes repeat. Find food, avoid becoming food, raise offspring, navigate the cycles of water, temperature and fire. A juvenile ornithischian tests the air before stepping out from under the shadow of a larger adult. A sauropod lifts its head higher, sensing distant thunder. A small mammal slips back into its burrow as a theropod's footsteps thud past above. Insects continue their quiet work in soil and bark. Crocodilians drift, patient, in brown water. These worlds of giants are not silent spectacles. They are functioning, breathing systems, intricate and ever-changing. And as they unfold over millions of years, another change is already underway, subtle at first, then more pronounced. Feathers, colours, and behaviours that hint at a future lineage taking shape within the dinosaurs themselves. For a long time, the image of dinosaurs in our collective imagination was narrow and sharp-edged. Grey or green, leathery skin, slow, tail-dragging giants, or roaring reptilian predators with bare teeth and empty staring eyes. Powerful, yes, but simple. Creatures of muscle and instinct more than nuance. The rocks tell a quieter, more complicated story. In certain ancient lake beds and fine-grained ash deposits, where mud once settled in still water and volcanic dust drifted down like snow, something delicate has been preserved. Around the bones of some small theropods, there is a halo of faint filaments, impressions so subtle that early fossil hunters often brushed them away without noticing. Under better light and with more careful eyes, those smudges resolve into structure. Branching fibres, arranged in rows, following the contour of a limb or tail. Feathers. Not always the long, stiff flight feathers we see on modern wings, but simple, hair-like filaments, tufts, and later, more complex vanned feathers. They appear in a range of species, tiny bird-like forms with teeth and claws, mid-sized runners with long tails, even some larger animals that never flew. From deposits in China, Mongolia, and elsewhere, a pattern emerges. Feathers were not an isolated innovation. They were part of the toolkit of many theropod dinosaurs. These structures likely began as insulation, trapping heat close to the body. A layer of fuzz would have helped small active animals keep their temperature more stable as they hunted, ran, and darted through changing climates. Over time, as feathers diversified into different shapes, they opened other possibilities. Display, camouflage, maneuverability in the air. And feathers are not the only clues that dinosaur skins and surfaces were more varied than once imagined. In a few lucky cases, the skin itself has left its mark. Skin impressions from hadrosaurs, ceratopsians, and other dinosaurs show pebbly scales, arranged in mosaics, with larger polygonal scutes set among smaller ones. The pattern changes across the body, finer on the flanks, larger on the tail, sometimes forming ridges or rows. One famous specimen of a duck-billed dinosaur preserves a crest of skin along its back, almost like a low, fleshy sail. Another hints at a series of raised knobs that might have broken up its outline. Some fossils suggest that feathers and scales could coexist on the same animal, scaly feet and tails, feathered arms and backs. Others show quill-like structures on the tails of ornithischian dinosaurs once thought to be fully scaly. The old division between reptilian skin and bird feathers becomes less clear. Instead, there is a spectrum, with different lineages exploring different combinations. Display structures add another layer of complexity. Horns, frills, domes of bone, crests of hollow tubes, tall neural spines rising from vertebrae. All of these grow from the skeleton, but they are anchored in living tissue, fed by blood, wrapped in skin or keratin. In life, they would not have been bare, bone-white shapes. They might have been sheathed in bright sheaths like the horns of antelopes, or in softer skin that flushed with blood when animals were excited or challenged. The elaborate frills of ceratopsians, with their scalloped edges and openings, may have signalled maturity, health, or identity, as much as they deterred attackers. From these structures, it is tempting to imagine vivid colours and patterns. Here, the evidence becomes both more fragile and more exciting. Most pigments do not fossilise well, but in some exceptionally preserved feathers, tiny capsule-shaped structures called melanosomes have been detected. In modern birds, the shape and arrangement of these organelles correlate with certain colours. Elongated ones often produce iridescent blacks and greens, Rounder ones can create browns or rufous tones. By comparing fossil melanosomes to modern databases, scientists have cautiously suggested that some feathered dinosaurs may have had dark, glossy plumage, striped tails, or contrasting light and dark patches. These reconstructions are still best estimates, not photographs from the past. Many colours, especially bright yellows and reds created by different pigment types, rarely leave direct traces. For scaly-skinned dinosaurs, the evidence is even thinner. At most, we can say that earthy tones, browns, greys, muted greens, would have fit many environments well, with possible patches of stronger colour on crests, faces, or tails. Like modern reptiles and birds, dinosaurs may have used colour to blend into dappled forest light, to signal danger, or to attract mates, but most of those palettes remain beyond our reach. Behaviour is even more elusive. Bones, feathers, and skin impressions show us what bodies could do, not always what they chose to do. Teeth and jaw shapes hint at diets, but not every hunting tactic. Trackways tell us how animals moved and sometimes whether they walked alone or in groups. Nesting grounds and brooding postures whisper of parental care. But sounds, rituals, daily rhythms, those are mostly inferred by analogy. Some hollow-headed dinosaurs with long, looping nasal passages may have used them like built-in resonating chambers, producing low calls that carried across distance, much as cranes or cassowaries do today. The deep chests and strong ribs of large theropods could have supported powerful vocalizations, yet the exact cries, songs, or rumbles are lost. Modern reptiles, birds, and even mammals offer models: hisses, grunts, booming calls, intricate songs. Dinosaurs, occupying so many roles in so many environments, probably filled the air with a variety of sounds, but we can only outline the range, not write the score. Within this haze of uncertainty, one connection grows clearer: the link between certain theropod dinosaurs and modern birds. Anatomically, the bridge is detailed and specific: wishbone-like clavicles, three-fingered hands that gradually fuse, backward-pointing pubic bones in some lineages, air-filled bones that lighten the skeleton, complex shoulders that allow the up-and-down stroke of a wing. Tiny toothed birds with long tails in the Jurassic sit on one side of the transition. Modern birds, with toothless beaks and short fused tails, sit on the other. Between them, a chain of feathered, ground-running, branch-perching, gliding, and eventually powered flying forms. Genetic and developmental studies in living birds show how scales can, under certain conditions, express feather-like structures, and how the timing of growth in the hand can shift the identity of digits. These lines of evidence, combined with fossils, suggest that birds are not merely descendants of dinosaurs in a distant metaphorical sense. They are a surviving branch of the theropod lineage, carrying forward ancient traits in transformed ways. This realization softens the boundary between dinosaur and bird until it almost dissolves. The sparrow on a windowsill, the heron standing silent in a marsh, the owl gliding soundlessly at night, all are, in a technical sense, living dinosaurs, shaped by the same deep processes that once gave rise to feathered hunters on Cretaceous floodplains. Feathers that once insulated small predators now generate lift. Display plumes that once signalled across fern forests now shimmer in courtship dances over wetlands and forest clearings. When we picture prehistoric Earth with this in mind, the scenes become richer. Not just hulking, uniform shapes, but animals with textures, fuzz and scales, quills and sheaths, moving through dappled light. Some flashed colours we can only guess at, others blended perfectly with mud, leaf litter, or snow. Their calls may have risen and fallen with the same layered complexity we hear in dawn choruses today. The fossils do not give us every detail, but they give us enough to know this. The age of dinosaurs was not a monotonous age of green and grey, of mindless roaring and stomping. It was a time of varied forms and subtle behaviours, of warmth and display, of social ties and individual lives. And within that diversity, one particular branch was already testing wings, practicing balance on narrow branches, learning to leap, to glide, and finally to fly. As feathers caught the air over lakes and forests, the rest of the world continued its own transformations. Seas shifted, mountains rose, climates cooled and warmed. The skies filled not only with early birds, but with other flyers that shared the air and the winds, each following its own path through a planet always in motion. Far from the forests and floodplains, another world was unfolding beneath the waves. During much of the Mesozoic, seas rose and fell again and again, flooding low continents, withdrawing, then returning. When sea levels were high, shallow sunlit oceans stretched over what are now prairies and deserts, turning the interior of continents into warm inland seas. In these waters, different rulers held sway. Long-body ichthyosaurs shaped like sleek dolphins with wide, staring eyes chased schools of fish and squid-like animals. Plesiosaurs and later pliosaurs with massive heads and powerful jaws moved their broad flippers in slow, steady strokes, cruising like underwater crocodiles. Pliosaurs with long necks threaded between, their tiny heads snapping up smaller prey in quick darting motions. Later in the Cretaceous, huge mosasaurs, marine lizards related to modern monitor lizards and snakes, took over many of the top predator roles. With double-hinged jaws and flexible skulls, they could swallow large prey whole, their tails propelling them with powerful sinuous strokes. Around them, ammonites drifted and spiraled, their coiled shells floating in the water column like living ornaments. Shoals of fish shimmered in shifting light. Tiny plankton bloomed in vast numbers, forming the base of marine food webs. Coral-like reefs rose in some regions, built by organisms that came and went as oceans warmed, cooled, and changed in chemistry. Above the water, the air was not empty either. Pterosaurs, the flying reptiles, traced arcs over coasts and open seas. Early forms had simple, elongated wings and long tails with diamond-shaped tips. Later, pterosaurs grew larger and stranger. Some had crests that rose from their skulls like sails, perhaps bright in life, catching wind and attention. Others, such as ajdarchids, would eventually grow to wingspans rivaling small airplanes, stalking shorelines and inland plains on long, stilt-like limbs when they were not in the air. These flyers were not just sky ornaments. They were fishers, insect hunters, scavengers, and perhaps stalkers of small vertebrates. They tied sea and land together, lifting nutrients from water to shore, from shore to cliffs. Their guano fed coastal ecosystems. Their bodies, when they fell, became food for scavengers below. Early birds shared this space too, darting among branches, skimming over lakes, or perching on rocky outcrops above surf. All of this unfolded on continents that were themselves drifting, very slowly but relentlessly. At the dawn of the Mesozoic, most land was joined in the supercontinent Pangaea, a single giant mass surrounded by vast ocean. Over tens of millions of years, rifts opened. Lava welled up along spreading centres. The supercontinent cracked into pieces that moved apart, forming new coastlines and new shallow seas. Where plates collided, mountain ranges rose. Where they pulled apart, volcanic provinces poured out sheets of basalt, sometimes in eruptions that may have lasted thousands of years, releasing gases into the atmosphere and nudging climates in new directions. As continents shifted in latitude, regions that had once been near the equator drifted toward higher latitudes. Others moved the opposite way. A forest that began in a humid belt might, over millions of years, find itself under cooler, drier skies. Ocean currents rearranged, redistributing heat. Monsoon systems strengthened or weakened as mountain chains grew or eroded. Dinosaurs, marine reptiles, pterosaurs, and early birds lived within these changes, not outside them. Plants changed too, and with them, entire food webs. In the early Mesozoic, landscapes were dominated by ferns, horsetails, and seed ferns, along with tall conifers and ginkgo-like trees. Under their shade, the ground was thick with spore-bearing plants, their fronds unrolling in moist, warm air. Many herbivorous dinosaurs fed on this vegetation, cropping fronds, stripping needles, rearing up to reach higher branches. By the middle to late Jurassic, seed plants diversified. Conifer forests spread across uplands. Cycads and bennettitels formed shrub layers, their stiff leaves and stout trunks dotting plains and slopes. These plants had their own strategies: tough leaves, chemical defences, and seasonal cycles that influenced when and where herbivores could feed. Then, in the Cretaceous, something new began to appear in the understory: flowering plants. At first they were small and modest, low shrubs and herbs with simple blossoms. Over time, angiosperms, as they're called, diversified rapidly. They evolved flowers to attract pollinators, fruits and seeds to entice animals to disperse them. Insects adapted in turn, with more specialized mouthparts and behaviors. Bees and butterflies would appear later, but even early pollinating insects began to weave tighter connections between plant and animal. As flowering plants spread, they changed the structure of forests and open lands. Some regions that had once been dominated by conifers and cycads became mosaics of mixed woodland and flowering thickets. Grasses were still in their early stages, but other angiosperms created layers of foliage at different heights, offering new kinds of food for different-sized animals. Browsing patterns changed. Jaw shapes and teeth in some herbivorous dinosaurs shifted subtly, reflecting diets that may have included tougher, more varied plant tissues. The Cretaceous world, especially in its later stages, was therefore anything but static. Sea levels rose high in some intervals, drowning coastal plains and creating warm, epicontinental seas where marine reptiles flourished. At other times, regression exposed new land, connecting habitats and allowing migrations. Volcanic episodes darkened skies, deposited ash over forests, and altered atmospheric carbon dioxide levels, with slow but real impacts on temperature and rainfall. Through all of this, dinosaurs lived not as isolated giants, but as parts of a planet-wide web. Their lives were linked to the productivity of plankton in distant seas, to the location of coastlines, to the spread of flowering shrubs and the rise of new insect lineages. A herd of hadrosaurs grazing on a Cretaceous floodplain was part of a chain that ran from microscopic organisms in inland seas to predators in the sky. A small, feathered theropod hunting insects among angiosperm leaves depended on the quiet partnership between flowers and their pollinators. A pterosaur fishing above a shallow bay was connected to the slow opening of an ocean basin thousands of kilometers away. Seen in this light, the age of dinosaurs is not a single, frozen tableau of familiar species under unchanging skies. It is a rolling sequence of worlds, each shaped by drifting continents, shifting seas, evolving plants, and changing climates. Some lineages held on for tens of millions of years. Others flickered briefly and vanished. But all of them, from the largest sauropod to the smallest plankton, moved within the same vast turning system. The ground beneath their feet, the air they breathed, the water they drank, none of it was fixed. The planet itself was in motion, and life, in all its forms, flowed with it, adjusting, diversifying, and sometimes fading away as new worlds took shape above the same enduring rocks. But even worlds that seem stable from a dinosaur's point of view are only pauses in a longer rhythm. By the late Cretaceous, the continents have drifted into shapes we would almost recognize. North America is splitting from Europe. India is an isolated traveller racing north toward Asia. Inland seas flood low-lying regions. Flowering plants carpet floodplains and hillsides. Tyrannosaurs stalk coastal swamps. Duck-billed hadrosaurs move in herds through forests of conifers and angiosperms. Triceratops browses under warm skies. Life is intricate and busy, but in the background stresses are building. Deep in what is now India, a vast volcanic province is erupting in pulses. Over hundreds of thousands, perhaps millions of years, enormous volumes of lava pour out, layer upon layer, forming what will later be called the Deccan Traps. Each eruptive phase releases gases into the air: carbon dioxide, sulfur compounds, water vapor. These gases alter the atmosphere, tilt climates, and may already be nudging ecosystems toward instability. Some regions grow warmer, others see shifts in rainfall, in seasonality, in ocean chemistry. Most species adapt or shift their ranges. Some fade away quietly. The world does not end. It changes, as it has so many times before. And then, on a day about 66 million years ago, something arrives from far beyond the clouds. A fragment of rock and metal, likely about 10 kilometers across, enters Earth's atmosphere at tremendous speed. In a fraction of a second, it compresses the air before it, heating it to incandescent temperatures. Then it slams into a shallow sea near what is now the Yucatan Peninsula. The energy released is almost beyond imagining. Rock and water are vaporized. A crater more than 150 kilometers wide is carved into the crust. Shock waves race through stone. Tsunamis surge outward. Molten debris and vaporized material are thrown high into the atmosphere and beyond, some of it arsing around the planet and falling back down. The scar it leaves, now buried under younger rock and sediment, will much later be named the Chicxulub crater. Around the world, in layers of ancient mud and sand, a thin band of clay will form at this time, rich in the element iridium, more common in meteorites than in Earth's crust. Mixed into that layer are tiny glassy spherules, shocked minerals, traces of soot. Together they form a global fingerprint, a quiet line in the rocks that says, something extraordinary happened here. What followed was not a single instant of annihilation, but a cascade of changes that unfolded over days, years, and centuries. Within minutes to hours, regions close to the impact suffer immediate devastation. Shock waves flatten forests, tsunami waves crash onto distant coasts. But far from the crater on other continents, animals may at first only sense a distant tremor, a subtle shift in the wind, a strange glow on the horizon. Then the sky begins to change. Debris falling back through the atmosphere heats the air. Many models suggest that for a brief time, this re-entering material may have ignited vegetation across vast areas, triggering wildfires on continental scales. Soot rises into the sky. Fine dust and aerosols from the impact itself spread quickly, wrapping the globe in a thin veil. Daylight dims. In some reconstructions, the world enters a kind of eerie twilight. Sunlight reaching the surface drops dramatically. Photosynthesis falters. Leaves that once turned toward the sun now face a dull, muted sky. Ocean plankton, dependent on light filtering down from above, begin to struggle. On land, temperatures may initially spike with fire, then drop as sunlight is blocked. Nights grow colder, seasons blur. Rain falls through this altered atmosphere. Some of it may be acidic, formed as gases from vaporized rock and impact-released compounds react with water in the air. Lakes and soils feel the sting. Forest canopies thin. Seeds and spores wait in the ground, biding their time. The true crisis is not only fire or rain or cold, but hunger. Plant growth slows or stops in many regions. Plankton productivity in the oceans declines. The base of the food web, both on land and at sea, is shaken. Large animals that need abundant daily food, especially big, warm-blooded creatures like many non-avian dinosaurs, face a rapidly narrowing window. Herbivores, already stressed by burned or damaged vegetation, find less to eat. Carnivores that depended on those herbivores begin to go hungry as well. In the oceans, ammonites once so diverse dwindle and disappear. Many large marine reptiles, mosasaurs, plesiosaurs, vanish. Coral communities change. Plankton communities shift dramatically, with some groups hit hard and others eventually rising in their place. On land, the pattern is uneven but severe. Non-avian dinosaurs disappear from the record. Large pterosaurs vanish. Many specialized reptiles, birds and plants do not survive. Yet not everything dies at once, and not everything dies everywhere. Some animals, especially smaller ones with flexible diets, seem to have found refuges. Burrowing mammals that could feed on seeds, roots, insects, or carrion may have weathered the darkest months hidden underground, insulated from extremes of heat and cold. Crocodilians, able to fast for long periods and live in water bodies buffered against rapid climate swings, persist. Some birds, especially those with ground-dwelling or seed-eating lifestyles, make it through, their lineages giving rise to the modern diversity of avians. Insects, fungi and bacteria continue their quiet work, breaking down the dead, cycling nutrients, preparing the way for new growth. Some plants survive as seeds, spores, or hardy individuals in pockets less affected by fire or acid rain. When light slowly returns and climates begin to stabilize, these survivors will spread into emptied niches. Scientists still debate the exact balance of causes. How much of the extinction came directly from the impact? How much from volcanism in the Deccan Traps? How much from longer-term climate and sea level changes that had already made ecosystems fragile? It may not be a single answer, but a layered one. Background stress setting the stage, volcanism tugging at climate and ocean chemistry, and then the asteroid delivering a sharp final blow. What is clear is that, over a relatively brief span in geological terms, the familiar cast of the Mesozoic, non-avian dinosaurs on land, mosasaurs and plesiosaurs in the seas, many lineages of pterosaurs in the air, vanishes. The age of dinosaurs in its old form ends. Yet even in this moment of loss, the story does not stop. In the shadows left behind, in burrows, in ponds, in dense patches of regrowing plants, small survivors wait, carrying with them the potential for a very different world to follow. For a while, the planet feels emptied. The roaring herds are gone. The air traffic of pterosaurs has ceased. Coastlines once patrolled by giant marine reptiles lie quiet under unsettled skies. In the years immediately after the impact, many landscapes are a patchwork of scorched ground, toppled forests and silty floodplains choked with ash and debris. Yet even in this quiet, life is not absent. It is simply lowered, hidden, waiting. In the soil, seeds lie dormant, thick-shelled, compact, carrying the memory of forests that no longer stand above them. Beneath riverbanks and lake margins, burrows hold clusters of small mammals, their bodies pressed together, hearts beating slowly as they ration stored food and fat. In muddy backwaters and sluggish channels, crocodilians float almost motionless, eyes just above the surface, conserving energy as they have for millions of years. The first years after the catastrophe are harsh. Food webs that once stretched elegantly from leaves and plankton up through herbivores to apex predators are broken. In many places the world is reduced to simple chains, detritus and fungi, insects and worms, small vertebrates that can make do with almost anything edible. Some plants respond quickly. Ferns, whose spores spread easily and germinate fast, often take the lead. On freshly disturbed ground, fern fronds unfurl across hillsides, a low green carpet reclaiming the ash. Palms and other hardy flowering plants sprout where moisture lingers. In places where roots survived beneath the scorched surface, shoots push up through the blackened crust, testing the returning light. Forests do not reappear overnight. They rebuild themselves leaf by leaf, sapling by sapling, over centuries and millennia. Early on, vegetation is patchy, and so are the animals that depend on it. Small omnivorous creatures move between islands of growth, feeding on seeds, insects, carrion, and each other. The age of giants has given way to the age of the small and flexible. Among the survivors are the birds, descendants of one resilient group of theropod dinosaurs. Many of the more specialized forms are gone, but some lineages with robust beaks and ground-feeding habits endure. They scratch through litter for seeds, probe rotting wood for insects, and flutter between low shrubs. Over time, these survivors will diversify into the immense variety of avian shapes and lifestyles we see today. But for now, they are mostly small, cautious, and few. Mammals, once confined largely to the ecological shadows of dinosaur dominance, find themselves in a world with space to grow. Before the extinction, many mammals were small insectivores, omnivores, or specialized gliders and burrowers. Afterward, with the disappearance of most large terrestrial reptiles, new opportunities open. The change is not instant. For tens of thousands of years, mammals remain modest in size, expanding more in diversity than in bulk. Different groups explore different diets and behaviors. Some focus on insects, others on seeds and fruits, some on scavenging. Their teeth begin to show new specializations. Their limbs adapt for climbing, digging, running. In the understory of gradually returning forests and along open floodplains, they begin to partition the world among themselves. Crocodilians persist along rivers and coasts, their generalist predatory habits and slow metabolisms well suited to lean, unpredictable times. Turtles endure as well, their shells offering protection, their varied diets giving them options in simplified ecosystems. In the oceans, sharks and bony fishes carry on, though the marine communities around them have changed profoundly with the loss of ammonites and many plankton groups. New kinds of microscopic algae rise to dominance, seeding the base of a different marine food web. As hundreds of thousands of years pass, climates gradually stabilize from the chaos of the impact and volcanism. Temperatures and rainfall patterns settle into new rhythms. Soils deepen as plants and microbes work together to trap organic matter. Rivers cut new channels through soft deposits laid down by post-impact floods. With each generation, life tests new forms, new strategies. By a few million years after the extinction, the landscapes of Earth would look lively again to any visitor. Forests of flowering plants and conifers stretch across many continents. Wetlands teem with turtles, amphibians, and fish. Birds fill the air with motion, if not yet with song as we know it. And among the branches and ground cover, mammals are no longer just small, furtive shapes. Some have become agile climbers, the ancestors of primates and other arboreal lineages. Others have lengthened their limbs and spines for running, beginning the long path toward hoofed grazers and cursorial hunters. A few experiment with larger body sizes, cautiously moving into the vacant roles once held by mid-sized dinosaurs. The largest animals are still small compared to late Cretaceous giants, but the trend is clear. With time and stability, body size can grow. Recovery, though, is not smooth or uniform. Some regions bounce back quickly, others lag for millions of years. Certain groups diversify explosively, then plateau or decline. Waves of cooling and warming, sea level rise and fall, continue to mould the possibilities. The world after the dinosaurs is not a simple replacement of one cast by another. It is a reweaving of the entire fabric, using old threads in new patterns. Birds still carry the legacy of theropod dinosaurs in their bones and feathers. Crocodilians echo the ancient archosaurs that once shared the world with T-Rex and Triceratops. Mammals, long minor players, now broaden into herbivores, carnivores, and everything in between. Plants, especially flowering plants, spread into forms and strategies that reshape soils, climates, and animal diets. In this long, uneven recovery, Earth is not returning to what was. It is moving into something else entirely, a Cenozoic world, one in which the descendants of tiny nocturnal creatures and modest seed-eating birds will eventually dominate forests, plains, and skies. The silence after the impact was real, but it was temporary. Beneath it, life was already composing a new kind of song, and so, when we look back across this immense story, from the first small dinosaurs weaving through Triassic undergrowth, to the towering giants of the Jurassic and Cretaceous, to the sudden darkness of impact and the slow, patient recovery that followed, a pattern begins to emerge. Worlds rise, worlds end, and yet, the deeper rhythm continues. Over hundreds of millions of years, continents drift like slow clouds of stone. Seas open and close. Climates swing from ice to hothouse and back again. Entire groups of creatures appear, flourish, and disappear, leaving only faint impressions in rock and in the genes of those who come after. Dinosaurs are one chapter, mammals another. We, humans, are only a page at the very end of the current volume. When you zoom out far enough, extinctions and recoveries become pulses. Loss, then renewal. Silence, then another chorus of unfamiliar voices. Each time, life does not simply repeat what came before. It experiments, it rearranges, it finds new ways to fill light and water and air. There is something quietly reassuring in that. The earth beneath you right now has endured impacts, supervolcanoes, shifting skies, and the rise and fall of oceans deeper than memory. Yet every time, in some sheltered hollow or hidden pool, life held on. It adapted, it changed, it continued. As you drift towards sleep, you are lying on a planet that has survived more than we can easily imagine. Our species is young and our future uncertain, but the story we are part of is old, resilient, and still unfolding. The rocks remember. The oceans remember. Forests, coral reefs, grasslands, even city parks are all temporary arrangements in a much longer dance. If you'd like to keep wandering through that deep time with me, you can gently tap like, subscribe for more quiet journeys like this, and share your thoughts in the comments. I'd love to know where you are listening from in the world, and what part of this long prehistoric night stayed with you. For now, you can let the ages blur together. Dinosaurs, early mammals, ancient seas, drifting continents, all sinking into a soft, distant background. The earth turns as it always has. Life endures as it so often has. And you can rest, carried for a moment on the surface of a very old, very patient world,